What's going on, Chem 20s? How's it going? Okay, today we're going to talk about net ionic equations. Now, what I want to talk about first is a very particular reaction. We want to take a look at a reaction between lead nitrate, lead 2 nitrate, and potassium iodide. Now, when we take a look at this particular reaction, you haven't seen it yet, but when we take a look at this particular reaction, we've got a test tube on the bottom, and it's got a clear colorless solution. That clear colorless solution contains potassium iodide. It's an ionic compound that's dissolved into the water. So it's dissociated, you can't see it anymore, it's dissolved, the ions have split up. Now up above here in an eyedropper, we've got lead 2 nitrate. That's also an ionic compound. It's clear and colorless. And it's also dissociated, so the lead 2 ions and the nitrate ions have separated from each other when they dissolve. So up here we've got lead 2 ions and nitrate ions. Down here we've got potassium ions and iodide ions. What I want you to do is I want you to watch this video, and I want you to see what happens and try and figure out what's actually happening, what's actually participating in this reaction, okay? Have fun, watch the video. Okay, hopefully that was a kind of enjoyable clip, even though it was a really short video. But what we've got here, we've got the lead 2 nitrate being added to the potassium iodide, and you can see this yellow cloudy stuff going on. I'm just curious, do any of you know what the word for this cloudy stuff is? It starts with a P. Yes, absolutely. It's a precipitate. And when we make a precipitate, that means we made a solid. So anytime your solution goes cloudy like this, you've made tiny little solid particles. And if we gave this solution enough time, those tiny little solid particles would settle down at the bottom of the test tube, and you would have a bunch of clumpy yellow solid at the bottom. Okay, so what we want to do is we want to try and figure out why this is happening. We want to try and figure out what's going on, what's participating in this reaction, what's not participating in this reaction. So what we got to do is we got to take some notes. I'm going to switch up my smartboard here for a second, and I'll see you in a second. Okay, Chem 20s, so today we're going to talk about net ionic equations. This is 7.1 in your notes, net ionic equations. Please get out a sheet of lined paper or whatever you're doing to take notes on. Net ionic equations. Now, a net ionic equation, instead of showing a balanced chemical reaction, what we're going to do is we're going to first write a balanced chemical reaction, but then we're going to change it a little bit, because some things in chemical reactions don't actually do anything. They're what we call spectators or spectator ions. So they're present, they are in the solution, you have added them, but they don't contribute to the chemical reaction. And what we want to do is we want to get rid of those spectator ions in our chemical equation, and we want to focus only on the things that are actually happening. You added something to something else, and what were the two things that actually reacted with each other? So the steps for writing net ionic equations. Number one, you have to write a complete balanced reaction. Hopefully you're okay with me abbreviating reaction as RXN. That's why we did practicing balancing and writing reactions yesterday. So step number 2, well, after we've got our complete balanced chemical reaction, what we're going to do is we're going to break up anything that can kind of be broken up, okay? So we're going to dissociate all high solubility ionic compounds and strong acids, because they're the things that split up 100%. So we're going to dissociate all high solubility ionic compounds and strong acids and that will make what we call a total ionic equation. Step number 3, we're going to cancel out any entities or any substances that appear the same on both sides of our chemical reaction. So we're going to cross off entities that don't change. And then number 4, whatever remains is what we call our net ionic equation. Write the remaining entities for our net ionic equation. So we're going to start off by talking about that particular reaction that we had there, and we're going to try and follow these steps. We're going to write a balanced chemical reaction, then we're going to split up anything that can be split up, and then we're going to cross off anything that doesn't change, and then we're going to rewrite the remaining substances as the net ionic equation. I do like a word of caution. These net ionic equations can be really wide. So start as far to the left on your sheet of paper as you kind of realistically can. So we're going to do our first example. That was lead 2 nitrate solution and potassium iodide. They were both solutions. So let's go ahead and let's start writing out step number 1, our complete balanced chemical reaction. So that's what I'm going to write here. I'm just going to say balanced reaction, just because we're going to separate things into very discrete steps. Okay, lead 2 nitrate. Well, when you take a look at your data booklet, right, lead is Pb. Lead 2 is Pb2 plus. Nitrate is NO3 with a minus charge. You're going to have to be really familiar with that. Nitrate is NO3 with a negative charge. You're going to see that a lot in different chemical reactions. And then potassium iodide. Okay, these are both ionic compounds. So potassium is plus and iodide is minus. So let's go ahead and write our balanced chemical reaction. We need 1 lead and 2 nitrates, PbNO3 2. We said it was an aqueous solution because it was a solution, so aqueous. And potassium iodide. Well, when we look at potassium iodide, we only need 1 K and 1 I because they're positive 1 and negative 1. So Ki, aqueous because it's been dissolved in water. And in a double replacement reaction, the metals, or the nonmetals, they swap places with each other. So the lead and the potassium are going to trade places. Now if lead 2 and iodide come together, right, the lead is going to be with the iodide. We need 1 lead and 2 iodides. So PbI2. We don't know what its state of matter is. And then the last one was the potassium and the nitrate are going to form a compound, KNO3. So let's take a look at our solubility table, and let's try and figure out what the states of matter are of these things, and then we'll balance it. So here we are. We've got our data booklet out. Hopefully you have your data booklet out. Pause the video if you need a little bit of time to get your data booklet out. But we're going to take a look at our solubility table. We're on page 6, so I'll just zoom in to our solubility table. And the first substance that we had was lead to iodide. So we're going to look for iodide first. You always, always, always look for the negative ion first. So we're looking on top for our negative ion. I see we've got iodide here in kind of the third or fourth column. So I got to look for lead 2 underneath it. And yes, absolutely, I find lead 2, which means it's going to be a precipitate because it's in the bottom row. So that first substance we had is going to be a precipitate. That's our solid. And that's a good thing. We saw a yellow solid forming, so that was our yellow solid. Now we got to look at potassium nitrate. So we'll go back to our data booklet. Erase that, erase that. You always look for your negative ion first. So we're looking for nitrate, NO3 with a negative charge. It's in the first column that has ions in it. So NO3 with a negative charge. Something you need to know about nitrate, and I'm going to be really explicit about this. When you look for nitrates, there are no nitrates that form precipitates. That's one of the reasons why you're going to see nitrates a lot, is because nitrates do not ever form precipitates. So you're never going to come across, if you see a compound that has nitrate in it, you just immediately write aqueous unless there's no water present. If there's no water present, then yeah, okay, sure, write solid. But nitrate, nothing, then it's in most, right? And because it's in the middle row, that means it's very soluble. It will be aqueous. So we go back to our notes and we write AQ for aqueous. Good. So that's our skeleton equation. That's not our balanced chemical reaction. In order to balance this chemical reaction, we got to take a look at, I always take a look at the most complicated substance. The most complicated substance in my mind is this thing right here. So 1 lead, 2 nitrates. I see 1 lead, but 1 nitrate. So I got to put a 2 in front of here. 2 potassiums means I need 2 potassiums, and our reaction is balanced. So that's step number 1. I know that took a lot of work, and honestly, step number 1 is the most work out of this whole situation. That's why we tried to balance chemical reactions yesterday. Okay, so we got a balanced chemical reaction. Let's take a look at our notes. Write a complete balanced reaction. That was step number 1. Step number 2, dissociate all high solubility ionic compounds and all strong acids. Well, any ionic compound at this point in time, any ionic compound that's aqueous, you will split it up. So dissociate it. We're not going to write a dissociation equation, but we're going to show the products of it being dissociated. So now we're going to show what we call a total ionic reaction. So lead to nitrate, when it splits up, we're going to get 1 lead. So the coefficient out in front is a 1, and there's only 1 in the formula. So 1 times 1 is 1. We're going to get Pb. Anytime something splits up, you must write a charge on it. It splits up because it turns into ions with a charge. So the lead becomes lead 2 plus, aqueous, and it's dissolved in water. Now we'll take a look at how many nitrates are going to be formed. The coefficient is a 1, and there's 2 in the formula. So 1 times 2 is 2 nitrates. you put the 2 out in front, just like in a dissociation equation. 2 nitrates. What this means is you have 2 independent nitrate ions. The nitrate ions, these 2 nitrates aren't stuck together, they're independent. So that's why the 2 is out in front. Perfect. Now we're going to break up the Ki, the potassium iodide, because it's high solubility ionic compound. 2 potassiums and 2 iodides. So 2 potassiums and 2 iodides. Now, those are all of my reactants. I'm trying to write really big so that you can see. So I'm going to write my products kind of down on the next level. You just have to understand all of these are reactants, and then the next stuff is products. Okay, what do we make? Well, we make lead 2 iodide. Are we allowed to split this compound up? No, we're not allowed to split this compound up because it's not a high solubility ionic compound. It's a solid. You saw in the video that it made a yellow precipitate. And that yellow precipitate obviously didn't dissolve. It didn't split up into its ions. So we'll write the whole thing as you see it here. If it's a solid, a liquid, or a gas, you can't split it up. So PbI2 solid. And then we're going to get 2 potassium ions and 2 nitrate ions, right? 2 times, there's 1 nitrate in here. So we can split that up because it's high solubility. 2 potassium ions. And every time something splits up, it turns into an ion, plus 2 nitrate ions. Hopefully that wasn't that bad. All we did was we took our substances from our balanced reaction and split them up if we could. So high solubility and strong acids are the only things that can split up. Now, that's our total ionic equation. Dissociate all high solubility and strong acids. Number 3, cross off any entities that don't change. If they don't change, they weren't involved in the reaction. They were just sitting there eating popcorn and just watching the show unfold. So let's try and see if there's anything in here that did change. Well, that didn't change. So the lead 2+ became lead stuck to iodide, so that did change. We're not allowed to cross it off. 2 nitrates, so 2 NO3 minuses, and at the end of the reaction, 2 NO3 minuses. Well, it doesn't look like it changed at all, so I'm going to cross that off. 2 NO3 minus, 2 NO3 minus. It's a spectator. It was present, but it didn't do anything. 2 potassium positive, 2 potassium positive. Again, it didn't change, so I'm going to cross it off. I'm going to ignore them. 2 iodide minus. In it, it hooked up with the lead 2+. So it did change. It's not exactly the same from start to finish. So what I'm going to do is now I'm going to write my net ionic equation. This is my net ionic equation that I'm about to write here. So I'm just going to rewrite everything that I didn't cross off. Lead 2+ didn't change. Pb2+ aqueous. It reacted with 2 iodide minuses. 2 iodide minuses. And it produced lead 2 iodide, so PbI2. That's our net ionic equation. A net ionic equation tells you what's actually involved in the reaction. What is actually participating here? Well, lead 2 ions were participating. Iodide ions were participating. They formed a precipitate, and we got lead 2 iodide as a result. A lot of the time, a question will ask you, what are the spectators? What are the spectator ions? In this particular reaction, the spectators are whatever we crossed off. So just list them off. Just tell me if something was or wasn't a spectator. So the first spectator I come across is nitrate. Yeah, it says 2 nitrate, but that's just because 2 of them were hooked up with lead at the beginning. Just tell me who was, not how many, who was involved, or who wasn't, I guess. So nitrate was a spectator, and then the other spectator that we crossed off was potassium ions. You're just listing, I don't care how many, we're just listing who wasn't involved in the reaction. Okay, so hopefully that makes sense. We're going to do another reaction here. I'm going to load up the video, and then we're going to try and talk about it. Okay, the next example you're going to see is magnesium with hydrochloric acid. Magnesium is a soft, silvery, malleable metal, and we're going to add it to some hydrochloric acid, and I want you to see what happens when we add the two together. So go ahead and take a look, and we'll come back and see. Good morning.
I got a question for you after you're done.
Okay. Okay, so hopefully that was an interesting reaction. We added the magnesium into a beaker, and then we added the hydrochloric acid. The hydrochloric acid and the magnesium, as soon as they interacted with each other, they immediately started to produce some bubbles. So we should see some bubbles happening in our particular reaction. So we got a new example. Hydrochloric acid and magnesium. Obviously, the hydrochloric acid was in a solution, so that's important. So first step is we have to write a balanced reaction. So let's go ahead and write a balanced chemical reaction. Hydrochloric acid, you should kind of know by now, really stereotypical acid, is HCl, aqueous. We're going to react that with magnesium. The magnesium is an element, but it's not part of Hofbrinkel, and it's not part of P4S8, so it's just magnesium solid. It's going to react in a single replacement reaction. Remember, metals kick out metals, and hydrogen is acting like a metal in this single replacement reaction. So the magnesium is going to kick out the hydrogen, so we're going to get some combination of magnesium and chloride ions. But when I look at it, when magnesium turns into an ion, magnesium's ion charge is 2+, so it's going to be 2+. Chloride ions are 1-. So I need 1 magnesium and 2 chlorides in order to balance the charges. So MgCl2, just kind of cross that off. And we're going to get the hydrogen kicked out as an element. Well, when hydrogen gets kicked out as an element, elements, we have to think of Hofbrinkel. Yeah, hydrogen's a part of Hofbrinkel, so it's H2. And we're going to take a look at its state of matter. So let's bring up the data booklet. Magnesium chloride, let's see if it's soluble or not. So we'll look for the negative ion first, chloride. We find chloride in the 3rd column. We look down and we don't see magnesium, so it must be a part of most. It is very soluble. That's great. So that thing is going to be aqueous. And that's exactly what we saw. We saw no precipitate forming. So the magnesium chloride should have stayed dissolved in the water. The hydrogen is going to be a gas when we take a look at our periodic table. So it's a gas. Now we need to balance this particular chemical reaction. Start with the most complicated substance. That's the most complicated substance. 1 magnesium, 2 chlorines. 1 magnesium, 2 chlorines. So we need to put a 2 out in front. Then 2 hydrogens, 2 hydrogens. Everything is balanced now that we have the 2 there. So, step number 1, write a balanced reaction. Good, fantastic. Step number 2, dissociate any high solubility ionic compounds and strong acids. No problem. So that's our total ionic equation that we're going to write. So 2 times 1 is 2 hydrogen ions. Hydrochloric acid is a strong acid. It will split up 100%. So strong acids you have to split up. Every time you split up something, you have to put charges on the things that split up. So 2 H's, but because it's split off of something, it's plus. And then 2 chlorines or chlorides, 2 Cl minuses. Magnesium's an element. It can't split up. Only high solubility ionic, only aqueous ionic, and strong acids can. So magnesium, solid. While magnesium chloride's an ionic compound, and it was aqueous, it was high solubility. So let's split it up. 1 times 1 is 1 magnesium. But because we split it up, we add a charge onto it. 1 coefficient, the coefficient of 1 times 2 is 2 chlorides. So 2 out in front, Cl minus, aqueous. And then hydrogen is an element. It can't split up, so we write it as H2 gas. We write it exactly the same way. Again, the only things that can split up are aqueous ionic compounds, high solubility ionic compounds, and strong acids. So now we're on to step 3. We're going to cross out anything that didn't change. The hydrogen ions did change. They went from H plus to H2 with no charge. They did change. So we're not going to cross them off. The chloride, 2Cl minus, 2Cl minus. Nothing changed, so we cross them off. That's a spectator. Magnesium went from Mg solid to Mg aqueous 2 plus. Is that a change? Did it change? Yeah, absolutely it changed. So we can't cross it off. It went from neutral to having a charge. That's a change. It went from solid to being dissolved. That's a change. It was involved in the reaction. So now we'll write our net ionic equation. I'm just going to extend the page here. So now we'll write our net ionic equation. So anything that did change, anything that we didn't cross off, we have to rewrite. 2H plus aqueous plus magnesium solid. Those are the 2 things that did change. Turns into magnesium ions and hydrogen gas. That is our net ionic equation. So the hydrogen ions turned into hydrogen gas, the magnesium solid turns into magnesium ions dissolved. And our spectator, our only spectator, was the chloride ions. Yeah, there were 2 of them, but we're just listing who wasn't involved. It doesn't matter how many, it just matters who was not involved in the reaction. So that's 2 examples, 2 pretty thorough examples with some videos to help go along. What we would like you to do is we'd like you to do some practice now, some practice doing some net ionic equations. There's going to be a key available for you, so let us know if you have any questions, and good luck. Have fun.